Hey guys, what's going on? So today we're going to be talking about the interpretation of the path integral. So last time we covered the path integral and its mathematical formalism. Today we're going to be talking about how we interpret the path integral. Now this is something that you probably haven't really come across in any sort of quantum mechanics or quantum field theory course. I'm going to try to come at this from a sort of a different perspective. And if you like this kind of content, please make sure to hit that like and subscribe button. Let's get into the material now. So we're talking about the interpretation of the path integral. So recall the definition. Actually, before I mention this, so as you notice, I have started a playlist going back onto symmetries of physics. With that playlist, the intent there is to come at physics from the perspective of symmetries, right? SO3, SU2 groups and all that kind of stuff. That is going to be on my Patreon page if you want early access, and it's also going to be coming out on my YouTube channel as well under that playlist. Anyways, let's get back into this. So we're doing the interpretation of the path integral. We're going to recall the definition of what a complex number is, right? We're going back to bare bones, and the complex number we can write as z is equal to e to the I theta. Now, if we take a look at this picture here, theta is the angle that subtends the number, right? So the number, a complex number, can be thought of as a vector, right? Where you have a component in the imaginary axis and a component in the real axis. And theta is the parameter that helps you define it's a parameter that you can attach to that number, right? So the number can be thought of as 2 points or one angle, right? That's one way of thinking about it. So when we're thinking about the action, what we derived earlier, right? So the action was an exponential of, or not the action, the path integral was an exponential of the action, right? And that action was sort of a weight on the various different types of paths that a particle can take through the state space. And that's what we have here, right? So taking direct analogy from a complex number, right? Z equals e to the I theta. E equals, or e to the I action, right, where the action itself can be thought of as an angle, right, in this imaginary space. So the action here is this angle, if you will, along an axis. So why is this helpful? Why is this useful? This means we can sort of parameterize a path in phase space and time. Again, we have our time axis with an action, right? So for every path, we attach an action to that path, right? And if this path is evolving in time, the angle will be evolving in time as well. The way we think about this is that the time drives the coordinates, right? The time drives the evolution of the states, which drives the action, right? So that's encapsulated right here, right? What I'm going to do actually here is just rebrand S as theta, right? Because we're thinking about this as an action, or as an angle, or we're thinking about the action itself as an angle in imaginary space, right? So two things we want to keep track of are this guy here, the change of the states with respect to time, and we're going to define that as being eta of t. And then we're going to define the change in the angle with respect to the change in the state, right? So, and that's going to be delta angle, right? This means that we can write delta angle times eta of t, which is here, right? So I'm just multiplying these guys here, and we see that this here is the change in the angle with respect to time. So nothing too fancy going on here, but we're going to get to something quite interesting. So we can integrate to get a total change. That's a change in the action over some time interval, right? So the way we do this is we integrate over time, right? Here, I'll write it out here. This guy here is dq dt, right? So dq dt, those two guys are going to cancel. Then when we integrate over time, right, that's going to get us, that's essentially going to get us the total sum in all the small angles, right? So dt is going to cancel out with dt. You can think of it like that, dt with dt, and then we're going to, this is the integral of all the angles, right? So that's going to give us delta. That's going to give us our angles. So that's how we think of this, right? So this object here, which I have right here, we'll see how this works. So if eta of t is the change in q with respect to t, then we can write this here, right? So what is this? This is the angle over some changed q equals q plus that change, right? So this is the change we're talking about, the change in q with respect to t, which we're going to say is equal to the angle at the original q, the original set of states at t, plus some change in the angle. Well, we wrote this guy over here as the integral for each little time interval, of dq here, or not dq, of d theta, right? So that should be an integral over d theta. That's what that, I think I forgot to put the integral there. But anyways, we diverge a little bit. I diverged a little bit. I didn't really diverge. We go here. So to this point, we replace this guy with what we calculated before, which is right here. All right, so I'm going to take this guy, I'm going to put back in its definition, and we have this guy. So this is the full-fledged action, right? So theta is the action, if you recall. Theta is the action, and then this is the change in theta when you change t, or you change the q's by a little bit. This is the term that we get. So here's where things get a little bit interesting, right? If any one of these guys is small, right? So if dq dt is small, then we have the integral essentially is very, very small, right? If this guy's small, then the integral is going to be small. Likewise, if this guy here is going to be small, right? That's right here. Then it's also going to, this term is also going to be very small. Essentially what we get is the action, the right side of the equation here, I can write the right side of the equation here. The action, the action right here is essentially or approximately equal to the action that didn't change, in which the states did not change. So we land here. Likewise, if this guy's small, and this over here is large, well, still, if this is sufficiently small, we can approximate again. Here that these two guys are equal. We really want these changes to be small, essentially, is what I'm saying. So we're really kind of just focusing on this point here. If these two guys are small, if there's a small change in time and there's a small change in this guy, both of these two guys are really small, then we can recover we can calculate, we can basically say that the action here is not changed by a lot. Okay. So what does this all mean? Well, if these guys are small, if there's a small change, we can come to this picture right here. If there's a small change in Q, what we said is that these two guys would be essentially equal, that this term here is really small, right? So if there's a small change in Q, again, this guy's really small, from the original, then the actions don't change very much. If there's a large change in Q, right? So here we have a larger change in Q's. Well, then that means that the actions will differ substantially, right? These two guys won't be equal. These two guys here will not be equal. And that's an example of destructive interference, right? So in one case, we have paths. This should say paths. Paths will constructively interfere. Again, constructive interference is when we have these two guys being small, or one of them sufficiently small to drive the other one down. Right? That's what these two guys. That's what these two guys in this table are for, are showing. And then, so we get this picture where all the paths that are near the say the classical path, or the path that's been unperturbed, all the paths that are near that one will constructively interfere, and we get an action that is large, and that large action defines the path that is most likely to be taken, right? So this is how we sort of transition from quantum to classical. And however, if the paths are far away from each other, or far away from the path that was not perturbed, again, then these paths will deconstructively interfere, and those are the paths that are less likely to occur, right? So the paths that are more likely to occur are the paths that are closer to the action, the smallest action, because they're all constructively interfering, whereas the paths that are further away from the lowest action principle, or from the lowest action, will deconstructively interfere. Those actions will deconstructively interfere with one another. And so you get paths that are close to each other that constructively interfere. Those are the paths that are most likely to happen. And then the paths that deconstructively interfere, those are the paths that are less likely to happen. And so this is how we make sense of quantum field theory, or this is how we make sense of the path integral formulation as we transition from quantum to classical. So that's essentially how this goes down, right? So we are at a point where we have talked about a lot in the book. There's really not that much left to cover, but there are a few topics left that we're going to be covering, and I predict it's probably going to be 1 or 2 more weeks before we're officially done with this book, in which case I will then be focusing on symmetric physics. And I also have some other playlists in the works that are also going to be coming out very soon. So if you like this kind of content, make sure to hit that like and subscribe button, and I'll see you guys in the next video.